Dear viewers, welcome to Finite Element Analysis. In this video, we are going to see the derivation of shape function for constant strain triangular element in Finite Element Analysis.
Hey to all, in this video section, I am going to show you the derivation of shape function for CST element. CST element, constant strain triangular element, decompose two-dimensional domain by a set of triangles. Each triangular element is composed by three corner nodes. Each element shares its edge and two corner nodes with an adjacent element. Counterclockwise or clockwise node numbering. Each node has 2 degrees of freedom, u and v. Displacement interpolation using the shape function and nodal displacement. Displacement is linear because three nodal data are available. Stress and strain are constant. At node 1, it has u1 and v1. At node 2, it has u2 and v2, and at node 3 it has u3 and v3 displacement. Totally the system has 6 degrees of freedom, so the stiffness matrix size will be 6 cross 6, and throughout the triangle the strain is constant at any point. That is why it is called as constant strain triangular element CST. An element of triangular shape is easy to develop and can be used to model irregular boundaries. The three-node triangular element was one of the first elements extremely used for continuum stress analysis. The function for displacement in the x and y coordinate direction can be described by the polynomial as shown for u x y. U of xy equal to a1 plus a2x plus a3y plus a4x square plus a5xy plus a6y square plus a7x cube plus. Here the a are constant to be found from the boundary condition on displacement. Notation for three-node triangular are shown in the figure. The coordinates are denoted in x and y. At node 1 it is x1 and y1. At node 2 it is x2 and y2. At node 3 it is x3 and y3. When you have a rectangular structure, then by drawing a diagonal, then you can split this into two CST elements. So this is how we have to discretize a structure into n number of CST elements. CST element, constant strain triangular element, decompose two-dimensional domain by a set of triangles. Each triangular element is composed by three corner nodes. Each element shares its edge and two corner nodes with an adjacent element. Counterclockwise or clockwise node numbering. Each node has 2 degrees of freedom, u and v. Displacement interpolation using the shape function and nodal displacement. Displacement is linear because three nodal data are available. Stress and strain are constant. At node 1, it has u1 and v1. At node 2, it has u2 and v2. And at node 3, it has u3 and v3 displacement. Totally, the system has 6 degrees of freedom. So, the stiffness matrix size will be 6 cross 6, and throughout the triangle the strain is constant at any point. That is why it is called as constant strain triangular element CST element. An element of triangular shape is easy to develop and can be used to model irregular boundaries. The three node triangular element was one of the first element extremely used for continuum stress analysis. The function for displacement in the x and y coordinate direction can be described by the polynomial as shown for u x y. U of xy equal to a1 plus a2x plus a3y plus a4x square plus a5xy plus a6y square plus a7x cube plus here the a are constant to be found from the boundary condition on displacement. Notation for three node triangular are shown in the figure. The coordinates are denoted in x and y. At node 1 it is x1 and y1. At node 2 it is x2 and y2. At node 3 it is x3 and y3. When you have a rectangular structure, then by drawing a diagonal, then you can split this into two CST elements. So this is how we have to discretize a structure into n number of CST elements. Then the boundary condition are at node 1 it may be subjected to f of x1 and f of y1, and at node 2 it may be subjected to f of x2 and f of fy2. At node 3 it may be subjected to f of x3, f y3. So here also the direction is very important. When the force is applied in the opposite direction, we have to consider the opposite direction. We will start the derivation of shape function. So first we have considered a trial solution, that is u is equal to a1 plus a2x plus a3y. Since it is two dimensional, I have considered y, and if only one dimensional degree of freedom is there, then we consider only that u. But here we have another degree of freedom, that is v. So that is why I have consider v also, but for derivation I am going to consider v, and finally we are going to merge v with the above equation. So we can convert this u into a matrix, that is u is equal to 1xy and a1, a2 and a3. So first we have to find out the value of a1, a2 and a3, and we have to substitute it in the equation to find out the value of u. We know that at the node r x is equal to x1, y is equal to y1. So as if I substitute x is equal to x1 and y is equal to y1, then I will get u1 is equal to a1 plus a2. In the place of x substitute x1, in the place of y substitute y1. Then similarly at x is equal to x2, u2 equal to a1 plus a2 x2 plus a3 y2. Then x is equal to x3 and y is equal to y3. u3 is equal to a1 plus a2x plus a3 y3. Now I am going to convert these three equation into a matrix. So u1, u2, u3 is equal to, in the right side I have a vector of a1, a2 and a3. I will get the matrix of 3 cross 3 matrix, and is 1 cross 1 and y1 1 x2 y2 1 x3 y3. So I have converted these three equation into a matrix. Now let me consider this u matrix. This is d matrix. This is a matrix. This is u d, and so u a and a. So u is equal to d into a. If I want to calculate a, then this is D will be coming here. That is why I have denoted in inverse U. So first let me calculate the inverse matrix of D. So D inverse is equal to transpose divided by modulus of D. So this is C transpose means this is a cofactor matrix of D. So we know that what is mean by cofactor matrix. So first we are going to calculate the cofactor matrix for D matrix. This is the D matrix as I denoted here. So this is my D matrix. So the C11 is you just neglect the first row and first column, and the sign are plus minus plus then minus plus minus then plus minus plus. So here first neglect 1 cross 1. So I will get x2 y2 x3 y3, then neglect this second, though I mean the second column and the first row, since it is 2 comma 1, so I will get minus 1 y1 1 and y3, then finally neglect 3 and 3, so I will get 1x 1x2. So similarly we will just neglect the row and column. We can calculate the cofactor matrix. So this is the cofactor matrix, and we have to calculate the transpose value of C. Transpose is equal to, I have converted the row into column. So now I am going to do this. I am going to name this P1, this is P2, this is P3. So similarly here it is Q1, Q2 and Q3 and R1, R2 and R3. So I have simplified the matrix. So now I have found out the value of C transfers. So here C transfers divide by modulus of D is there. So I have calculated C transfer. Now I am going to calculate modulus of D. So it is modulus of 1x 3y 3. So when you consider a triangular element, then find out the area of triangular element. The equation is, so the triangular element x3, so the equation is 1 by 2 1 x1 y1 1 x2 y2 1 x3 y3. This is equation for calculating the area of a triangular element. Then equal this, so these two are equal. So A is equal to of is there. So I have multiplied modulus of D with, I mean A with 2. So modulus of D is equal to 2 times the area. So now I can substitute it here. So that is in the equation of C. Transpose divided by modulus of D. So modulus of D is 1 by 2A, and the C transverse value I have substituted it here. So finally substitute these two in the equation number 2 in this equation. In this equation we can substitute it. Now this is my A1, A2 and A3, and we know that after calculating A1, A2 and A3 we can substitute it in the first equation. So first equation is U is equal to 1x y A1, A2, A3. Okay, so I am going to substitute this matrix in this equation. So I have substituted it, then I can multiply these two matrix. So this matrix is size 1 cross 3 and this is of size 3 cross 3. So I will get 1 cross
3 matrix. So that is P1 plus Q1 into X plus R1 into Y divided by 2A. The 2A is there. Similarly P2 plus Q2 into X, R2 into Y divided by 2A. Similarly P3 plus Q3 into X and R3 into Y, and the shape function equation. We know that it is U is equal to N1 U1 N2 U2 plus N3 U3, and U is, you can convert this equation into a matrix. So it is N1 N2 N3 U1 U2 U3. Now you can equate these two equations. So let us consider this as equation A and this equation number 2. So if you equate these two values, then n1, this is my n1, and this is my n2, this is my n3. So n1 value is p1 plus q1 and dx plus r1 into y divided by 2a, then n2 is equal to p2 plus q2 into x plus r2 into y divided by 2a. Then n3 is equal to p3 plus q3x plus r3y divided by 2a. So this is the value of n1, n2 and n3. So these are all the shape function value, and here what is p, what is q, what is r is important. So that is going to be your formula. So this p1 p2 and p3, q1 q2 q3, r1 r2 r3. So just remember the equation. So the first point, you start with assumption of the trial solution, then you just substitute this boundary condition, though then you convert it as a matrix, then from the matrix you just calculate a1 a2 a3 value. I have calculated it here, then I have substituted it in first equation to find out the value of the shape function. So with the help of this shape function, further we can calculate the strain displacement matrix and stress strain relationship matrix.
Thank you for watching my video.